In this video we are going to see about time harmonic field. So time harmonics is a topic which we are seeing after finding the power of the electromagnetic waves. So first we will derive Maxwell's equations. From Maxwell's equation we will find what is the wave equation. From wave equation we will find the power associated, and then we have to move to time harmonic field. In time harmonic field, first we have to consider the Faraday's law, from which Maxwell's second equation has been derived. So by Faraday's law, the varying electric field induces magnetic flux, and this magnetic flux is directly proportional to the EMF induced over there. So this has been given in Maxwell's equation as del cross E is equal to minus dou B by dou T. And now this del cross E, whenever taken as a curl function over the entire space, we have to take it in terms of curl function, where the determinant of I, J, K vector over X, Y, Z direction has been taken. So for this we have to put del cross E is equal to I vector, J vector, K vector, dou by dou X, dou by dou Y, dou by dou Z, Ex, Ey, Ez. On expanding it, it will be I vector into dou Ey by dou Y minus dou Ey by dou Z minus J vector into dou Ez by dou X minus dou Ex by dou Z plus K vector into dou Ey by dou X minus dou Ex by dou Y. If we consider this electric field intensity is acting on Y direction and propagating in X direction, the resultant will be in Z direction, and so we will be having K vector into dou Ey because it's acting in Y direction, and so dou Ey, and propagating in X direction, so it's varying with respect to X, so K vector into dou Ey by dou X we are getting. This Ex and Ez will be 0 then, because as it is acting in Y direction, we are having only dou Ey by dou X into K vector. By time harmonics, we are having dou Ey by dou Faraday's law, we are having dou Ey by dou X is equal to minus dou Bz by dou T. And we already know the relation between electric field intensity and magnetic flux density, which are both perpendicular to each other. The propagation will be given as Ey is equal to sin x minus Vt. So see here, Y is propagating in Y direction and with respect to X. It's given over this graph, and here we are having the Ey component, which is sinusoidal in nature, and so we are having the E and B will be E and B, that is perpendicular to each other. To take it as, we are having Ey equal to sin x minus Vt. On differentiating Y with respect to X, that is dou Ey by dou X will be cos x minus Vt. But we are, by Faraday's equation, we are having dou Ey by dou X equal to minus dou Bz by dou T, and so we equate this cos x minus Vt to minus dou Bz by dou T. So from this, if we take Bz, it will be negative integral of cos x minus Vt into dt. Integrating cos x minus Vt will give you minus sin x minus Vt by t. This minus gets cancelled, and so we are having sin x minus Vt by t. But if we see magnetic flux density over a single period, that is one period time, it will be B is equal to sin x minus Vt. And the relations for magnetic flux densities will be B is equal to mu h and B is equal to 1 by Vh by wave equation. So, but V is equal to 1 by root mu epsilon, and so it's equated to root of mu epsilon into E. Equating these two B values, we are having mu h is equal to root mu epsilon into E. So taking the mu over here, E is equal to root of mu by epsilon into h. In free space it will be written as E is equal to root of mu naught by epsilon naught into h, where mu naught is equal to 4 pi into 10 to the power minus 7 and epsilon naught is equal to 8.854 into 10 to the power minus 12. On taking the fraction and square root on account, it will give you 377. So 377 ohm means it will be characteristic impedance for free space. So E is equal to Z naught H gives you the time harmonic field effect. So this is your derivation for time harmonic field effect. Thank you.